I'm Professor Devendra Singh taking this course on machine design, and this is our ninth lecture where we have reached to the theories of failure. We have discussed in last lecture theories of failure, what is theories of failure, why it was required, इनकी ज़रूरत क्या थी और कितनी theories of failure हैं. So, principal stress theory we have already discussed. Now, this lecture including these three topics basically is maximum strain theory, graphical representation. We have discussed the maximum strain theory in the last lecture. So, here we will try to learn the graphical representation of maximum strain theory. Then we will move to the maximum shear stress theory and its graphical representation. Then finally, we will move to the maximum distortion energy theory and its graphical representation. ये तीन पॉइंट हम इस लेक्चर में कंप्लीट करने का प्रयास करेंगे. मैक्सिमम स्ट्रेंथ थ्योरी जैसा कि हम लास्ट लेक्चर में डिस्कस कर चुके हैं, सॉरी, कि किसी भी बाई एक्सेल या ट्राई एक्सेल स्टेट ऑफ स्ट्रेस में किसी भी बॉडी पे अगर स्ट्रेन उसका यील्ड पॉइंट के स्ट्रेन के करीब या उससे आगे पहुंचती है, उसके बराबर पहुंचती है, तो हमारा मटेरियल फेल होने वाला होता है. ये हमारा प्रेडिक्शन, वी कैन प्रेडिक्ट ऑन दैट बेसिस. अब इस थ्योरी को हम ग्राफिकल रिप्रेजेंटेशन की तरफ चलते हैं. तो देखते हैं विद फैक्टर ऑफ सेफ्टी 1, जब फैक्टर ऑफ सेफ्टी 1 हो तब रिप्रेजेंटेशन कैसे होगा. तो सबसे पहले देखेंगे जो इक्वेशंस हम डेराइव कर चुके हैं लास्ट लेक्चर में. दिस इज biaxial state of stress sigma 1 sigma 2 is the modulus of elasticity of the material on which we are analyzing. Nu is the partition ratio. So, this is an tensile, both stresses are of same nature, compressive or tensile. Sigma E t here we have used, this is the yield point stress or elastic point, specifically I have used here to avoid एक कन्फ्यूजन कि यील्ड पॉइंट और इलास्टिक पॉइंट तक हमारा हुक्स लॉ वैलिड होता है और वहाँ पे सिग्मा इज डायरेक्टली प्रोपोर्शनल टू एप्सिलॉन. सो अल्टीमेटली we will replace it by yield point stress. So, this is equation and E will be cancelled out here, and this is final equation. This is sigma 1 minus nu sigma 2 is less than or equal to sigma E t or S y t, yield point in tension or elastic point in tension. Then this is on the plane of sigma 1 sigma 2, it will be line equation, it is a single degree equation. So, it will be represented graphically by a line. We will consider these conditions. When sigma 1 and sigma 2 both are of tensile, then this is the equation I have discussed. One side it will elongated, एक तरफ को अगर हम इसे बढ़ाएंगे तो उसका lateral direction में जो डायमेंशन है वो रिड्यूस होगी. दैट इफेक्ट वी कैन एनालाइज एंड आप सब इसको स्ट्रेंथ ऑफ मटेरियल में अच्छी तरीके से समझे भी हैं. और फिर मैंने इसको रिप्लेस भी किया है यहाँ पर. यहाँ इस्तेमाल किया है कोई कन्फ्यूजन ना हो कि हम सिग्मा अपॉन ई ले रहे हैं. फिर हमने ये एज्यूम कर लिया है कि ये नज़दीक हो. फिर ये भी संभव है कि सिग्मा 1 ज़्यादा हो तो ये, और सिग्मा 2 अगर बड़ा है सिग्मा 1 से तो इक्वेशन बनेगी ये. तो हमें दोनों कंडीशंस, जितनी भी पॉसिबल कंडीशंस हैं उनको कंसिडर करना पड़ेगा टू ड्रॉ. अब सिग्मा 1 एंड सिग्मा 2 आर कंप्रेसिव इन नेचर, सेम नेचर में इक्वेशन वही रह जाएंगी. राइट यहाँ पे हमने एस वाई सी और एस वाई सी लिखा है, इसको मोड ऑफ माइनस एस वाई टी. So, this S y c is equal to S y t, but negative in nature. So, this is another assumption you can have here. Then graphical representation if both tensile or compressive. So, these are the equations. Then this is sigma 1 sigma 2, this is plus sigma 1 sigma 2 plot is this, and then we try to mark the points. This is the intersection origin point, then S y t, this is minus s y t upon nu. These points we will get from here. अगर सिग्मा 1 पे हम कोऑर्डिनेट ज्योमेट्री में पढ़ें, अगर हम एब्सिसा पे कुछ पॉइंट लेना चाहते हैं तो हम कोऑर्डिनेट y कोऑर्डिनेट यानी कि ऑर्डिनेट को हम 0 रखेंगे. So if we put sigma 2 here 0, then sigma 1 is equals to syt, and in compression it will be minus syt. Similarly, if on ordinate axis means sigma 2, then we will put sigma 1 is equals to 0 and we will get a point minus syt upon nu. So, this is equation is a linear equation. So, join these 2 points syt and minus syt upon nu, we will get a line. This is a line, this is the equation for this, and similarly for other equations we will get syt and minus syt upon nu, join it, this is another line. Then similarly in compression also these are other lines, we will get these 4 lines, and the enclosed area in these 4 lines will be the safer zone. This is the graphical representation of maximum strain theory. So, this is the safe zone. If our loaded point is lying in this bluish zone, then our design is safe. Otherwise, as per as this theory of failure, Venice and Venice theory, we will predict कि this design will be going to fail. Now, comparison. Why can Rankine theory not be used for biaxial stresses opposite in nature? The answer we will get from this explanation, and it is very important. This is maximum strain theory or Saint-Venant theory. Now, we will plot another yellowish. This is maximum principal stress theory. If you see why Rankine theory, this yellow is the Rankine theory. If you consider the Rankine theory, according to Rankine theory, up to this point you will consider the material is safe, but as per as the strain theory, this is the maximum point up to which it can be strained without any failure. So, this zone will become a danger zone. Similarly, here also this zone will be the danger zone, and this is also a danger zone, this is also a danger zone. Similarly, here also this is also danger zone, this is also danger zone. So, this is ये एरिया डेंजर जोन में आ जाता है और सेफ जोन कहता है प्रिंस रैंकाइन थ्योरी के अकॉर्डिंग ये सेफ है, बट स्ट्रेन थ्योरी के अकॉर्डिंग ये यहाँ से आगे आप डिफॉर्म कर नहीं सकते हो मटेरियल को. सिमिलरली हियर आल्सो दिस पोर्शन is unsafe according to maximum strain theory, and according to Rankine theory this is in safe zone, yellow region में है. अब देखते हैं इधर, this is plus sigma 1 positive abscissa means tensile stress, here minus sigma 2, this is the region, this is the 4th quadrant. So, the state of stress is having the opposite nature of these stresses. So, Rankine theory will become dangerous to use in this state. Similarly, here sigma 2 this is tensile, sigma 1 is compressive, opposite in nature, and this zone we will get the danger zone as per as strain is concerned. So, due to this reason, it is always advisable we should not use the Rankine theory when biaxial state of stress composed of two opposite nature of stresses. Similar explanation you can make for the same nature of stresses, tensile you should not use this maximum strain theory. Here this will become the danger zone, here it will become both are compressive. So, same on the same line you can explain why you can not use maximum strain theory, maximum principal stress theory. In fact, maximum strain theory is obsolete nowadays. This is having only the academic purpose. ये केवल academic purpose के लिए मैंने बात की है. maximum strain theory हम डिज़ाइन में इस्तेमाल नहीं करते हैं। डिज़ाइन में केवल हम 3 थ्योरी ऑफ फेलियर इस्तेमाल करते हैं। एक प्रिंसिपल स्ट्रेस थ्योरी, रैंकन थ्योरी जो हम ब्रिटल मटेरियल्स के लिए इस्तेमाल करते हैं, दैन मैक्सिमम शियर स्ट्रेस थ्योरी, मैक्सिमम डिस्टॉर्शन एनर्जी थ्योरी, मैक्सिमम शियर स्ट्रेस थ्योरी और डिस्टॉर्शन एनर्जी थ्योरी हम डक्टाइल मटेरियल के लिए इस्तेमाल करते हैं। सो we will move to the next, maximum stress theory, maximum shear stress theory. A statement you can write. Similarly, as we have written the statements for the previous two theories of failure, the material is going to fail as soon as the maximum. This is shear stress theory, so we will compare the maximum shear stress theory, कितना इंड्यूस हुआ और किस पॉइंट पे स्ट्रेस किस नेचर का शियर स्ट्रेस थ्योरी है। सो नेचर शियर होनी चाहिए, किस पॉइंट से कंपेयर करना है, यील्ड पॉइंट से कंपेयर करना है। तो स्ट्रेस थ्योरी you can write the material is going to fail as soon as the maximum shear stress theory or maximum shear stress in any direction reaches a value equal to or greater than the shear stress at yield point in tension during the uniaxial tensile test. यही सारी लाइन्स हम हर थ्योरी ऑफ फेलियर के लिए, स्टेटमेंट के लिए अगर हम कहते हैं तो यही लिखते हैं। और यहाँ पे ये पोर्शन और ये पोर्शन हमें याद रखना चाहिए कि किस तरीके की हम बात कर रहे हैं, स्ट्रेन की बात कर रहे हैं, प्रिंसिपल स्ट्रेस की बात कर रहे हैं, शियर स्ट्रेस की बात कर रहे हैं या डिस्टॉर्शन एनर्जी की बात कर रहे हैं। So this portion, if you are using, if you want to write a statement for the maximum distortion energy, so you will replace simply maximum shear stress by maximum distortion energy theory, and it should be compared with the distortion energy at yield point. So you can write, you can remember one statement, you can frame the statement for all theories of failure, बट हमें ये ध्यान देना चाहिए कि ये हम बात कर रहे हैं कि हम याद रख सकते हैं, लेकिन हमारी अंडरस्टैंडिंग क्लियर होनी चाहिए कि शियर स्ट्रेस क्या होती है, प्रिंसिपल स्ट्रेस क्या होती है और डिस्टॉर्शन एनर्जी क्या है, वॉल्यूमेट्रिक चेंज के लिए एनर्जी क्या है, ये हमारी क्लियर होनी चाहिए। अगर ये क्लियर नहीं होगी तो केवल हम एक स्टेटमेंट लिख पाएंगे, वी विल नॉट बी एबल टू अप्लाई these concepts in our design. So, for designing purpose, it is very essential to have a very clear concept about these all these quantities. Sorry. So, now we will consider there is a block which is subjected to three mutually perpendicular stresses sigma 1, sigma 2, sigma 3, and here I will consider these are the principal stresses sigma 1, sigma 2, sigma 3, and then maximum shear stress may be given as strength of material में आप लोगों ने पढ़ा है कि अगर हमें तीन प्रिंसिपल स्ट्रेसेस मालूम हो सिग्मा 1, सिग्मा 2, सिग्मा 3, तो हमें मैक्सिमम शेयर स्ट्रेस की मैग्नीट्यूड कैसे डिसाइड करते हैं। मैक्सिमम शेयर स्ट्रेस की मैग्नीट्यूड डिसाइड करने के लिए हम सीधा सा हम मोर सर्किल भी आप बाई एक्सल स्टेट ऑफ स्ट्रेस में ड्रॉ करके यू कैन फाइंड आउट, बट दिस इज इन ट्राई एक्सल स्टेट ऑफ स्ट्रेस द मैक्सिमम प्रिंसिपल स्ट्रेस and minimum principal stress का difference divided by 2 is the maximum shear stress. So, the formula this is from your strength of material tau max shear maximum shear stress sigma max minus sigma minimum divided by 2. These sigma max and sigma minimum, these are the principal stresses. Please note these are the principal stresses, right. Then you will find the maximum shear stress induced in the material whatever state of stress given or subjected. On the same basis, on using the same formula, what is the magnitude of shear stress at yield point? So, at yield point in uniaxial state of stress, so whatever stress you induce in the direction that reaches to the value of SYT, that is yield point in tension, that is sigma 1, sigma 2, sigma 3, these are 0. in uniaxial state of stress. This that is why maximum is sigma SYT, sigma to 0, then this is SYT by 2, tau y t is SYT by 2. Then if we consider sigma 1, sigma 2 and sigma 3 are 3 mutually perpendicular. So, tau max क्या हो सकता है sigma 1 minus sigma 2 by 2 induced, but the permissible कितना हो सकता है जिसके बाद हम फेलियर प्रेडिक्ट कर देते हैं, that is SYT by 2. So, 2 2 maybe will be cancelled. So, sigma 1 minus sigma 2 should be less than equal to SYT. Plus minus means it this may plus if it is in tension and minus if it is in compression. So, sigma 1 minus sigma 2 minus sigma 3 less than equal to plus minus SYT, sigma 3 minus sigma 1 less than equal to plus minus SYT. This is with factor of safety 1, and the condition when sigma 1 is the largest and sigma 2 is the least. Here sigma 2 is largest and sigma 3 is the least. Here sigma 3 is largest and sigma 1 is the least. Then these are the 3 possible conditions. In fact, you will write with tension and compression, you will get these are the 6 equations. Sigma 1 minus sigma 2 is less than equal to plus SYT, sigma 1 minus sigma 2 is less than equal to minus SYT. So, in fact, these are the 6 equations we are getting for maximum shear stress when the body or the material is subjected to 3 mutually perpendicular sigma 1, sigma 2, sigma 3 principal stresses. So, these are the equations. If we want to incorporate some factor of safety, so factor of safety, you will divide this strength by factor of safety. So, if factor of safety is there, then tau y t मैं कहता हूँ कि परमिसिबल कितना होगा, that is equal to SYT upon 2, this is tau y t and divided by factor of safety, right. So, here this is, now we will move to the next maximum shear stress theory. So, sigma 1 is less than equal to plus minus SYT if sigma 2 is equals to 0 from the same equations. These are the points. So, we move to the graphical representation. So, if we have considered sigma 1 minus sigma 2 is less than equal to plus minus SYT with factor of safety 1, then sigma 1 is less than equal to plus minus SYT. You can plot 2 points on sigma 1 or on abscissa axis. So, this is equation of line where sigma 1 is less than equal to SYT. This is one line. Similarly, other line, this is sigma 1 is less than equal to minus SYT. So, इसके बीच में अगर हम कोई पॉइंट लेंगे इन दोनों लाइन्स के बीच में, तब हम कहेंगे कि ये पॉइंट हमारे सेफ जोन में है एज फार एज sigma 1 is and minus sigma 1 is concerned. Similarly, sigma 2 is less than equal to plus minus SYT. So, on sigma 2 axis you will mark these 2. So, this is safe. Now, sigma 1 minus sigma 2 is less than equal to SYT. So, this is again a single degree equation. This is y is equals to m x plus c in this form, and you will draw the point. So, where it will intersect with the x axis and y axis, coordinate geometry की मैं बात कर रहा हूँ. अब x को sigma 1 से replace कर दीजिए, y को sigma 2 से replace कर दीजिए, then you will get where you can draw this line. This is now very simple to draw. So, this is the line sigma 1 minus sigma 2 is less than equal to SYT, and similarly for other sigma 1 minus sigma 2 is less than equal to minus SYT. So, now this zone within this these points, this enclosed zone is the safe zone. So, A, B, C, D, E, F, these this is a safer zone, or the green portion I have shown here. This is the safe zone as far as the maximum shear stress theory is concerned. This is the safe zone, and ये जो बाकी हमारा डॉटेड रेक्टेंगुलर स्पेस और स्क्वायर, इफ एस वाई टी एंड एस वाई सी आर सेम देन दिस इज ए स्क्वायर. सो दिस स्क्वायर जोन ए बी सी डी ई एफ हमने यहाँ लिखा है, तो जी दिस इज दिस मीन्स तो ए जी डी एच, this is maximum principal stress theory. So, we can see according to maximum shear stress theory, we cannot use for the opposite nature. ये maximum shear stress theory is used for the ductile material. Ductile materials are weak in shear. So, we have to check always it should be successful against the shear. So, that is why shear stress theory is applicable for the ductile material. If you want to some factor of safety, then this region will be reduced and more conservative design we will get from this theories of failure. This is safe zone. Now, comparison that I have already discussed for principal stress theory, this is what? This is the maximum strain theory. Then above it, this is the maximum shear stress theory. So, maximum shear stress theory gives more conservative results, and this is maximum principal stress theory. So, maximum shear stress theory is more conservative as compared to the maximum strain theory and the maximum shear stress theory. Saint-Venance theory, this is the maximum shear stress theory, Guest and Truscott theory, दूसरा नाम, and Rankine's theory, that is maximum principal stress theory. Now, the maximum distortion energy theory. So, I have already mentioned, मैंने पहले ही बताया स्टेटमेंट में कोई कन्फ्यूजन नहीं होना चाहिए, जैसे वहाँ पे shear stress था, यहाँ पे द डिस्टॉर्शन एनर्जी थ्योरी इस एनर्जी के साथ हम एक वर्ड इस्तेमाल करते हैं दैट इज स्टोर्ड. सो distortion energy theory stored in the material reaches to the distortion energy theory stored by the material at the yield point in tension in a uniaxial tensile test, then we say material is going to be fail. In fact, the total strain energy in the material when it is subjected to the stress will composed of two components. U is the total strain energy, U d is the distortion energy theory, and U v is the strain energy theory. Sorry, U is the maximum strain energy stored in the material, U d is the maximum strain energy stored due to the distortion, U v is the maximum energy, strain energy stored in the material due to the volumetric change. So, you can use this equation. So, what is U? That is half epsilon into sigma into epsilon, half times sigma into epsilon. So, sigma 1 total strain energy, half sigma 1 multiplied by epsilon 1 plus half sigma 2 multiplied by epsilon 2 plus half sigma 3 multiplied by epsilon 3. Epsilon 1 is what? This is the net strain in the direction of stress sigma 1. So, epsilon 1 is what? Epsilon 1 कितना हो गया? Sigma 1 upon E minus nu sigma 2 upon E plus sigma 3 upon E, and similarly you will get epsilon 2, epsilon 3, and it should be multiplied by sigma 1 and half. इसको एनर्जी में सिग्मा 1 के डायरेक्शन में करना चाहते हैं तो इसको मुझे टोटल को सिग्मा 1 बाई 2 से मल्टीप्लाई करना पड़ेगा. अगर मैं इसे मल्टीप्लाई करूंगा तो मुझे ये टर्म सिग्मा 1 स्क्वायर की मिलेंगी, सिग्मा 2 स्क्वायर की मिलेंगी, न्यू आएगा. दैट एक्सरसाइज यू कैन डू and ultimately you will get this expression for the total strain energy. Now, U d is the distortion energy we need to calculate, and this is your volumetric strain energy half times sigma v multiplied by epsilon v, right. So, sigma 1 plus sigma 2 plus sigma 3 divided by 3, epsilon 1 is equals to epsilon 2 epsilon 3. You will get what is sigma v and epsilon v. So, you will get this expression for the u v. Now, after solving this, we will get this expression for distortion energy. This is the expression for the distortion energy, right. So, for uniaxial state of stress sigma 2 and sigma 3 हम इसको 0 करें, then u d कितना बनता है uniaxial state of stress के लिए. So, sigma 1 एस वाई टी के बराबर करें टेंसाइल टेस्ट के लिए अगर हमने निकालना है तो सिग्मा 2 एंड सिग्मा 3 हम 0 के बराबर रखें, then you will get u d y t is equals to 1 plus nu upon 6 e multiplied by 2 times of s y t square. You can solve it and you will get this is the result. So, it will be 1 plus nu upon 3 e into s y t square. This is at yield point. Now, it should be compared with the u d. U d should be the distortion energy stored in the material under the effect of the sigma 1, sigma 2, sigma 3 must be less than or equal to u d at the yield point. So, this is your successful condition according to a maximum distortion energy theory. If you put the expressions, then you will get finally this half into sigma 1 minus sigma 2 का whole square plus sigma 3 minus sigma 1 का whole square plus sigma 2 minus sigma 3 का whole square should be less than or equal to s y t square, where s y t is all the problem is subjected to factor of safety is equals to 1. If you solve it, you will get this equation, and for the biaxial state of stress, if sigma 3 is equals to 0, you will get sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 less than or equal to s y t square here, and if factor of safety you want to incorporate, then s y t will be divided by factor of safety, then the equation is this. And if you are aware about the analytical geometry, then this is the equation of an ellipse. So, we will try to represent it on the graphical plane sigma 1 sigma 2 biaxial state of stress in the next lecture. So, this is for today. So, thank you very much.